Ariela, we are very lucky to have you. She works at Intel Labs. She drives forward-looking research on edge networking and compute. Prior to Intel, Ariela was vice president at InterDigital, and she has a proven track record of leading technology and product teams in multiple areas, including wireless communication and AI. And we are so lucky to have you. Thank you so much, Ariela. Please take it away.
Yeah, so many thanks, Manya, for the introduction, and good morning, everyone. And Vince, you said your work was more impressionistic. Mine will be even more inspirational, or motivational, if you will. So I would like to talk today about challenges in machine learning and a way forward. And we can just skip this. So I don't know how to get rid of this line here, but sorry for this. So the takeaway from this slide is now that we are ready for the third wave in AI. And for this, I would like to share a presentation by DARPA, where they identify three waves of AI. The first one is handcrafted knowledge. The second one is statistical learning. And the third one is contextual adaptation. And we are today in the second wave, and which is based on deep neural networks, where we compute the outputs from the data and we adjust the weights based on backpropagation, which is very heavy computationally. And this is quite powerful in terms of perceiving and learning, but has some deficiencies in terms of abstracting and high-level reasoning. And I just chose one favorite slide from this presentation of DARPA. So basically, it shows that it's statistically impressive, but individually unreliable. So this little young boy is holding a toothbrush, but the AI thinks he's holding a baseball bat. So, let's just list what we perceive as challenges of machine learning today. So computer efficiency, we have big models with millions of parameters, memory overhead, we have a large memory footprint for models. In terms of data efficiency, typically we need like thousands of data passes to train. Online learning, actually it's very difficult to learn while streaming online data. Robustness, it's prone to susceptible to adversarial perturbation. And as for knowledge representation, it's not amenable for representing knowledge. And here are some charts to demonstrate this. So the chart that you see right now addresses the first two challenges. So where we see on the left-hand side that compute needs doubles every 3 to 4 months. And on the right-hand side, memory capacity grows by 10x every year. In terms of robustness, it's really susceptible to perturbations. So for example, and I'm not going for, this is the MNIST set that Vince has referred to, but for example, in this beautiful flower here is classified by Jaguar by just really small distortion that wouldn't bother the human mind at all. And finally, in terms of cognition or knowledge representation for cognition, deep learning lacks the cognition reasoning ability to address tasks fundamental to human intelligence. So for example, in terms of description, the human mind can easily tell in this picture what is the likely, what is the profession of the person in the picture. And from point of causality, what may have been the reason for his fall. And in terms of prediction, what is likely to happen next. And from point of view of cognitive state projection, right? How this person is feeling about this, what his experiences, and from terms of explainability is how why does the AI think that the person feels this way? So those are things that are easily done by the human mind, but current deep learning methods and representations cannot address this. I would like to introduce you to hyperdimensional computing. I'm not sure who of you is aware of this new paradigm in AI, but we view this as a promising new paradigm for energy efficient, noise robust, and fast alternative to standard machine learning. A remarkable feature of this that it works on both numeric and symbolic data. And here I'm listed a few of the benefits. It's intrinsically noise robust, right? It's easy and fast to train. It's well understood theoretically. It's easy to construct complex structures from simple ones, and it's also well suited to highly parallel and energy efficient hardware. And in the literature, many applications have been reported. A lot of classification tasks, right? Image classification, object recognition, DNA sequencing, activity recognition, speech recognition, and then also clustering, regression, and recommendation system. Let's just talk about some of those properties. Where this intrinsic robustness coming from? It actually comes from a property of random vectors in high dimensional space that they are approximately orthogonal to each other. And this chart on the right demonstrates this property. And of course, the level of orthogonality improves as we increase the dimension of the vector. And in this case, the dimension is 10,000, which is a typical length of hyperdimensional vectors for HD compute. So the robustness is really the fundamental enabler is this property of random vectors in high dimensional space. And then I mentioned something about fast learning, enabling online learning from streaming data. So just to give you a sense, the learning here is very different from the learning in deep learning. It's actually no backpropagation is done. And just assume for a minute that you have a simple classification problem. You really want to classify between cats and dogs. And just assume for a minute that you find a way to encode an image of a cat, right? So you really create just one hyperdimensional, high-dimensional vector that is the cat prototype. And you do this by an operation that is called bundling, right? So you bundle all those single image encodings to one cat prototype. And similarly, you generate a dog prototype. And then for the inference stage, right, you encode the image in the same way, and then you just close the most similar hyperdimensional vector. And, you know, as for the elements of the vector, they can be binary 0, 1, they can be bipolar plus minus 1. But the bundling is simply, it's for the most cases is simple addition type of an operation. So it's very parallelized and simple, right? So this is great to explain, really, or to illustrate how, to what extent it's different from machine learning based on deep neural networks. But I mean, it has some deficiencies in terms of accuracy and also capacity, how many different classes you can represent. So there are other schemes. This is a simple perceptron scheme that you actually, while you bundle those images, in this example, we have 4 different classes. Now, this is still part of the training, right? So you assume that you have a label image, And then if you do this inference and you come up with the correct answer, you actually add or bundle this new vector into the class prototype. But if actually it's misclassified, it's a mistake, incorrect match, then you actually subtract it. That gives better performance. And finally, what looks very promising is this addition and subtraction are now done based on the uncertainty or confidence level in the classification. And this will require some iteration, so it's no longer one-shot learning, but it's still few-shot learning. It's still very fast, simple, and very promising. So this is about learning. Now, maybe the most intriguing property of HD compute, its ability to represent data. So, and complex data structure that you build from simple data structure. So how can we do this? Just a couple of examples here. And I'll go a little bit to more details in the subsequent slides. With a single high-dimensional vector, we represent a very complex tree structure or a visual scene, like you see here. And then we have three operations that we use to form and manipulate data structure. I already mentioned bundling, which is addition, similar to addition. So we use those terms interchangeably. Multiplication, which is binding, and permutation. And together they form an algebra over the space of high-dimensional vectors. So permutation sounds scary, but typically it's implemented by one bit shift, one element shift of the vector. So let's look a little bit deeper into this. So let's talk about visual scene, and this is a toy example, right? So imagine this toy example where in the scene, we can have any of 10 different digits, and they come in 7 different colors, and they can have either like 9 different positions, 3 vertical and 3 horizontal positions. And now we want to describe this scene. So the way we do, we have an encoding or hyperdimensional representation of the digit 7, and we bundle it with the representation for the color, the cyan, and then we also have representation for each of the position. So, this is done by bundling. So we bundle all those attributes together, and then to describe the entire scene, we use bundling or addition, right? So we have 23 atomic parameters, 10 for digit, 7 for colors, 3 for vertical and horizontal, and we create the description of the visual scene. So it looks like a very simple scene, but even this simple scene has more than 250 million possible scenes, right? And yet with hyperdimensional representation, we can represent it by a single vector. Now the feature extraction, it's actually still an active area of research. You can do it by a simple neural networks, and you can do it also by HD techniques. I don't have time to get into it, but when we outline the remaining area for research, I definitely mention this feature extraction or encoding. So let's go to the second toy example where we represent trees, right? And here trees are similar. We still use the same operation of bundling and binding to represent the tree, but here we also need to represent the level in the tree, which we can use the permutation operation to describe the level. So for example, if we want to describe this leaf B, we can look at this second line here and we say, well, B, we get to be by first left, and this is just first level, then a right, and this is the second level, and another left, and this is the third level, and the level is represented by this permutation operation row in this picture. So, and this is very powerful because here we use this permutation to represent the level of the tree, but similarly, we can use the same operation to use the time if we have a time series type of a data. So, hopefully I gave you some taste of hyperdimensional computing. We don't have enough time to go to further depth. But in summary, while deep learning enabled major breakthroughs in AI, we now encounter major challenges in scalability, sustainability, robustness, and reasoning. And HD computing shows great promise to address these challenges, and call for action, and where we need additional research is in the following areas. Encoding for complex multi-scale data, while we have good results for relatively simple data, including recommendation system, then for images, which tend to have features and different scales, we need better methods. Then we have some publication about using HD for high-level reasoning, but they are not at scale. So scalability is important here. I mean, we have anecdotal evidence of robustness, but we would like to get some theoretical guarantees. And finally, there is a lot of opportunities in optimization for evolving and emerging computing platforms, because it's really, the computation is very different for deep learning and obviously requires other ways of optimization. And there is one point that actually I didn't mention here, but to relate to federated learning, we see also a great potential for federated learning that is based on HD computing rather than traditional deep networks. So this concludes my talk. Thank you very much. And I'll be very happy to answer any questions.
Thank you so much, Ariela. I really, really love the talk.
Yes.
Is Miriam back on? All
yes,
right,
I am.
here.
I have joined by phone. I'm so sorry. My home network died at the most inopportune time.
Yeah.
Sorry about that. And thank you, Manya, for taking over the mantle. And I was just going to say something about Ariela, but I think I don't need to say it anymore because now everybody's seen it, which is the fact that Ariela has this amazing ability to just know how everything fits in, and more importantly, how everything should fit in. And really what the directions of technology and the major problems coming up are, and obviously you've seen it with your own eyes at this point. Ariela, I had a question about, you've talked about some of the challenges. If you were to identify what is your main challenge right now in networking to allow the sort of vision that you just described, maybe the top two, what would those be?
Well, I would say the ability to learn while you're streaming data, because currently deep networks are not amenable for online fast learning with good accuracy. That's probably the main challenge that we see. But I mean, if you want me to refer to wireless data, that's probably wireless network, that's probably the main challenge. The other challenge is not so much related directly to wireless network, is the ability to enable high-level reasoning and cognitive tasks.
And how much of that is the network and how much of that is the learning algorithms?
I think the network, I think it's the learning algorithms, right? The network, okay, let me rephrase. The cognitive and high-level reasoning is not so much the network, it's really the data representation. because the data representation itself is not very amenable to enable this cognitive and high-level reasoning. Regarding networks, I would say that actually HD computing has a very high promise because of its robustness. And there are even some work and some research done on privacy, right? So in sense, because you encode everything in this high dimensional vector, and then you can do a lot of the computing in this high dimensional space, it also gives you some additional privacy benefits. So the connection to wireless networks, its robustness to noise, and there are some early work on this that demonstrates this robustness. Did I answer your question, Muriel?
So I think I think to some extent you did, but I guess so. I think you did with the aspect of the noise. But do you think that it's mostly that the learning algorithms are not keeping up with the capability of the networks, or are they ever being underserved currently by the capability of the networks?
I would say the network learning algorithms are so computationally heavy that they just cannot be done while you are streaming data. So if you envision like offline learning, right, or a learning in an aggregator, which is more capable, that's fine. But if you want to do it really at the lower end devices, right, I don't think you currently can do it.
So maybe this gets a bit into the point that Vince made.
Yes,
about
and
the
I would try to point out that there is some synergy there in the sense that federated learning is very promising and very important for networks, right? And you can do it even more relevant, in my opinion, by using HD computing rather than traditional deep learning.
Okay, so actually there's a question in the chat from Ephraim Mojes, and asking, by using hypercomputational method versus machine learning, how is the solution complexity reduced?
How it's reduced? So again, I didn't present research results, but we have some very practical problems where we are able to reduce the model size by 300x and the memory footprint by 100x. And this is just preliminary, and the potential for further reduction with the same accuracy. So very promising, but again, we are in just beginning of the road, and my purpose of presenting this in this forum is to encourage more people to look at it, because we see a great promise, but we need participation for the academia, because there are some theoretical challenges that we need to address, and other challenges as well.
So actually, let me also reprise one of the topics that was at the end of Vince's talk, which is that of privacy. And, you know, I'm sure you're aware that there's been quite a dust up in Europe around FLoC, right? Because at least the versions that were being proposed to be deployed were found not to be GDPR compliant. Mm-hmm. And when you see that, particularly, you know, in industry, in terms of, you know, what are impediments then to adoption of whatever you may be coming up with, do you see some benefits of the hypercomputational methods you're proposing in that regard?
Absolutely, yes. And there are some publications in this area. I can give the references. It's just early. It has promise there, right? Mm-hmm. It has promise there. Some people claim that it has the potential to replace or a very simpler alternative to homomorphic encryption, right? But it's still early. I mean, so this is relatively an early field, I would say. Yeah. Although it was proposed in 2009 by Pentic and Nerva of Berkeley, and it was called then VSA, Vector Symbolic Architecture. So this is really the same name, but now it has re-emerges with new potential, I would say.
There's a question from Yongzhao Chen on the chat. It seems that the encoding of the raw data is a key step for the success of HD computing. Can we have some automatic way to encode the data under different contexts and environments, or do we need to be manually generating the encoding algorithm?
That's actually an excellent question. Currently, the state of the art is that it's custom for each problem, which is not a desired. But I didn't have time to mention in my talk, there is nice relationship to kernel-based methods, and HD computing can be looked as an approximation for one of those kernels. And I think this could be a good way to make it more automated way to encode the data. So, but again, that's why I mentioned in call for action research area, we see a pathway to where more automated type of encoding, or at least not per class of data. It could be for images, it's one way, maybe for accommodation system, it's another way. But, and the key could be kernel-based methods, but then we don't have all the answers yet.
Okay, thank you. Thank you very much. Yeah, okay. And if you said that you were basically issuing this as the way you put it, sort of a call for action, which I think is a great thing exactly for this kind of workshop. That's precisely the type of the type of message we want in these sorts of mixed workshops. And if you were to say in terms of field of use, what do you think are going to be in the near and medium term the fields of use that are going to benefit most from this?
By far, the one that is very relatively near term is recommendation systems. But then I don't know if there is so much research there. But I think if we are able to apply HD to images, right, and that's still and get the same accuracy of deep network. We are not there yet, so that could be the next thing. But currently, and then there. Another way is to look at hybrid, right? That you start with HD representation and follow up by more traditional deep learning, and then you can end up with lighter networks. So this also shows promise.
Fantastic. Okay, thank you very much. And actually, it's great that you're. I can't on the phone. I can't clap, but I'm moving excitedly, and to thank you. And so I really want to thank you very much. And Manya, I can see is clapping. So thank you very much, Ariela. That was truly motivating and fun. I really
thank you, Ariel, for your kind words, and thank you for everyone for your good questions and a great workshop.